I have discussed two important methods for, or you can say two important theories for testing of hypothesis. One was the Neyman-Pearson theory, where we considered the UMP test, uniformly most powerful unbiased tests, etc., and another was the likelihood ratio test. Now, while discussing the UMP test, we had seen that there are situations for which UMP tests do not exist. For example, if we consider the hypothesis testing problem in a single normal population, sigma square is equal to sigma naught square against sigma square not equal to sigma naught square. We showed that no test can be UMP. However, in these situations, what we showed that we can actually have UMP unbiased test. That is the test which is uniformly most powerful among all unbiased tests. Now, a similar concept, we have also seen that there are situations where we cannot derive UMP unbiased tests also. Now, our concern is to introduce one more such concept. Now, there are problems which you can think as a naturally symmetry, like when I say H naught mu 1 is equal to mu 2 when we are considering two normal populations. Now, when I say mu 1 is equal to mu 2 and against mu 1 not equal to mu 2, then my test function should be symmetric in the first sample and in the second sample, that is x i's and y i's. And if you remember the form of the test function also, it is given as a function of x bar minus y bar, modulus sign is coming, divided by square root of say s 1 square plus s 2 square, etc. There, if you interchange the roles of x i's and y i's, then you get the same value, that same result should come, because the numbering of the population should have no influence on the actual testing procedure and also the conclusion which is drawn from there. This is called symmetry. So, likewise, if you consider the one way analysis of variance test which I derived for testing equality of the means, mu 1 is equal to mu 2 is equal to mu k. In that test, if you see, we got the ratio in the numerator sum of squares and in the denominator another sum of squares was there. In that sum of squares, if we interchange the order of the samples, you still get the same test. So, this test is also invariant under, you can say, interchange of the subscripts. This is called symmetry. So, this concept I introduced in the estimation when we were discussing point estimation, and we showed that we can define what is an invariant or equivariant estimator and derive the best in the class of equivariant estimator. Sometimes it is possible, sometimes it is not possible. In a similar way, we introduce invariant tests. Therefore, if within the class of invariant test we can find UMP, then it is the UMP invariant test or uniformly most powerful invariant test. So, I will give a brief description of this theory here and derive UMP invariant test for a couple of problems here. I will not get too much into details here, because the detailed tests for various problems in the normal distributions, etc., we have derived thoroughly in the likelihood ratio, UMP unbiased testing procedures. So, here I will only give example, but I will consider the concept in a proper form. So, the first condition that you require is the invariant family of probability distributions. Now, this concept of invariant family of probability distributions I introduced in the part 1 of this course when we were discussing the point estimation. So, you may revise from there. For the sake of completeness, I will give brief description of these concepts once again here. So, we start with let x have probability distribution, say p theta, theta belonging to omega, and let G be let me write here script theta as the notation that I have been following earlier. GB transformation from x into x. So, this is the sample space. We assume G is 1 1 and 2. So, we say that the family of distributions p theta, theta belonging to omega is invariant under the transformation G if for every theta belonging to script theta, this is actually script theta as the parameter space. If for every theta there exists a theta prime belonging to script theta, such that whenever x has probability distribution p theta, g x has probability distribution p theta prime. We use the notation theta prime is equal to g bar theta. That means, we are saying p theta g x belonging to A is equal to p g bar theta x belonging to A. Or we can say p theta g inverse A is equal to p g bar theta A, or p g bar theta g of A is equal to p theta of A. We can write in various forms this condition here. We have discussed the various examples related to invariant families of distributions under various transformations. If you remember, if I consider normal distribution with mean theta and variance unity, and I consider translation, that means, in place of x, if I consider the distribution of x plus c, then x plus c has normal theta plus c one distribution. So, if theta is a real number, theta plus c is also a real number. So, this is an example of a translation invariant or location invariant family of distributions. Similarly, we have exponential, gamma, etc., as the scale parameter families. So, I refer the readers of this course to my earlier lecture in the same course on point estimation, where we have given examples of all these situations. I will not be repeating these things here. So, the parameter space theta remains invariant under G, that is, we say preserved under G if G bar theta belongs to omega theta for all theta belonging to theta. And if for every or any theta prime belonging to theta, there exists theta belonging to theta such that G bar theta is equal to theta prime. So, we can say that G bar theta is actually equal to theta. That means, application of this transformation leaves the parameter space invariant. And the transformations G of on omega, they are 1:1. The transformation g bar of omega into omega, they are 1 1 provided the distributions p theta corresponding to different values of theta, they are distinct. That is, p theta 1 is equal to p theta 2 implies theta 1 is equal to theta 2. We have the following lemma: let g and g prime be transformations which preserve theta. Then g prime g and g inverse defined by composition, that is g prime g of x is g prime of g of x and g of g inverse x is equal to x, also preserves theta and it satisfies g prime g equal to g prime bar g bar and g inverse bar is equal to g bar inverse. These results I had given in the estimation part also. So, let me just briefly sketch the proofs here. These results I am calling 2 and these equations I am calling 1. Let us look at the proof of this. If x has a distribution say p theta, then g x has a distribution p g bar theta and g prime g of x, that is equal to g prime of g of x. This has distribution p g bar prime g bar of theta. Also, if I consider directly g prime g of x, this has distribution p g prime g bar theta. So, g prime g bar must be same as g prime bar g bar. And similarly, we can prove the other part also. So, in a very similar way this can be proved. Now, we introduce what are invariant testing problems. We say that the problem of testing h theta belonging to omega h against k theta belonging to omega k remains invariant under a transformation G if G bar preserves both omega h and omega k and let us consider C be the class of transformations let C be the class of transformations G for which G bar theta is equal to theta and G bar theta h is equal to theta h, and let G be the smallest class of transformations containing C and such that G and G prime belonging to G implies that G prime G belongs to G and G inverse also belongs to G. Then G is a group of transformations containing C and by lemma 1 preserves theta and theta h. So, any class C of transformations leaving the problem invariant can therefore be extended to group G, and from lemma 1 it follows that G bar is also a group and G bar is a homomorphism of G, but of course, not necessarily homomorphic, isomorphic, not necessarily isomorphic. Now, I define what is an invariant function. If you remember, in the estimation we defined a covariant estimator. Now, I am defining what is an invariant function. So, phi is an invariant function with respect to a group of transformations G if phi of G x is equal to phi of x for all x and for all G. That means, the function does not change the value if x is transformed from x to G x. Now, based on this I define maximal invariant. If x 1 x 2 belongs to x, we say that x 1 is equivalent to x 2 under G, that is we write x 1 equivalent to x 2 mod G. If there exists G belonging to G such that x 2 is equal to G of x 1. Now, this relation, the relation this is actually equivalence relation. That means, it is reflexive, symmetric and transitive, because every element is related to itself or equivalent to itself using identity transformation. Since G is a group, identity element belongs to that. Now, if I say x 1 is equivalent to x 2, so I say x 2 is equal to G x 1, then x 1 is equal to G inverse x 2. That means, x 2 is also equivalent to x 1, because G inverse also belongs to G. Thirdly, it is also transitive, because if I say x 1 is equivalent to x 2 and x 2 is equivalent to x 3. So, there exist say G 1 and G 2 such that x 2 is equal to G of x 1, G 1 of x 1 and x 3 is equal to G 2 of x 2. So, x 3 then becomes G 2 G 1 of x 1. So, x 1 and x 3 are also equivalent. So, this relation is an equivalence relation, and hence it partitions x into equivalence classes. We call these equivalence classes as orbits. Thus, an invariant function is constant on orbits. Let me take an example, say x is the real line, G is consisting of two elements, say E and G, where G x is minus x, and this is the identity element. Okay. So, minus x x for x greater than 0, so greater than or equal to 0, this is set of orbits, because with respect to this transformation x G of x becomes minus x. So, and G of minus x will become x. So, these two elements will be related, and of course, for 0 it is equal to 0. So, that is a singleton set. So, this is the collection of orbits for this problem. Now, I define what is a maximal invariant. So, a function T x is said to be maximal invariant under G if first T x is invariant under G and secondly T x 1 is equal to T x 2 implies that x 2 is equivalent to x 1, that is x 2 is equal to G of x 1 for some G. In other words, we can say that T x is maximal invariant if it is constant on the orbits and secondly it takes different values on different orbits. So, in a given problem we can restrict attention to the maximal invariant. Let me give one elementary result in this direction. I will call it theorem 1. Say let T x be maximal invariant with respect to G, then a necessary and sufficient condition for phi to be invariant is that it depends on x only through T x. That is, there exists a function h for which phi x is equal to h of T x for all x. So, a function will be invariant if and only if it is a function of maximal invariant. That means, it depends on x only through the maximal invariant function. Let me give a proof of this. If phi x is equal to h of T x for all x, then if I consider phi of g x that is equal to h of T of g x, that is equal to h of T x, because g x is equal to x here, that is equal to phi of x. So, phi is invariant. On the other hand, if phi is invariant and if T of x 1 is equal to T of x 2, then x 2 is equal to g of x 1 for some g, and therefore, phi of x 2 is equal to phi of x 1, and so phi depends on x only through T x. Let me give example of maximal invariance. Say X be the n-dimensional Euclidean space and G is the group of translations. That is, G consists of G C, C belonging to R, where G C of X is given by x 1 plus c, x 2 plus c, x n plus c. Then T x is equal to x 2 minus x 1, x 3 minus x 1 and so on, x n minus x 1. This is maximal invariant. For example, you take say x I minus x 1 is equal to x I prime minus x 1 prime. Then this will imply x I is equal to x I prime plus x 1 minus x 1 prime, that is equal to x I prime plus c. Of course, in this problem, here if I write say T 1 x is equal to say x 1 minus x n, x 2 minus x n and so on, x n minus x n, or if I consider say T 2 x that is equal to say x 1 minus x 2, x 2 minus x 3, x n minus 1 minus x n. So, these are also maximal invariants in this problem. We may write, so they are one-to-one functions of each other. If I consider say n is equal to 1, then there are no invariants. The whole space is single orbit. That is, for any 2 points there exists a transformation of G taking one point to another. In such a case, the group G is said to be transitive group. The only invariant functions are then constant functions, that is phi x is equal to c. Let me take a scale group. Say G is the group of scale transformations G C x is equal to C x 1, C x 2, C x n for C positive. This is called the scale group. Then in this case you see T x is equal to say x 1 by x n, x 2 by x n and so on, x n minus x n, or T 1 x is equal to say x 2 by x 1, x 3 by x 1 and so on, x n by x 1. So, these are all maximal invariants. Let X be n dimensional Euclidean space and G is the set of n factorial permutations of the coordinates of X. Then the order statistics T x that is equal to x 1, x 2, x n. This is maximal invariant. Let me consider another example. We consider the group of linear transformations G A B x is equal to A x 1 plus b and so on A x n plus b, where A is not 0, b is any real. This is the linear group or affine group. In this case, T x is equal to say x 1 minus x n divided by x n minus 1 minus x n and so on, x n minus 2 minus x n divided by x n minus 1 minus x n. This is maximal invariant. We may derive other maximal invariants in this problem. Now, after introducing this theory, I introduced the concept of UMP invariant tests. Like we had the so here I have already introduced the invariant function. So, if a test function is invariant, it is called an invariant test, and then we consider the UMP, whether it is UMP or not. So, we introduce UMP invariant tests. Now, what will be an invariant test? I have proved the theorem that an invariant function is actually a function of the maximal invariant. So, if I consider all the tests which are based on the maximal invariant, then it is the class of all invariant tests. So, the class of all invariant tests is the class of tests depending only on the maximal invariant. So, in a given problem, we firstly derive the maximal invariant and consider the tests based on that only. So, let me give an example here how to derive this. So, I am considering a random sample from a location family, from say f x 1 minus theta and so on x n minus theta. It is a location parameter distribution, and let us consider the hypothesis. I am writing here 2 here, because when we are doing the testing problem, I can consider 2 particular forms here. So, H is that density is say f naught and H 1, k is the density is f 1 say, all right. So, this problem is invariant under the translation group. You remember the translation group that I introduced just now, that is the translation group was given by the set of transformations x 1 plus c, x 2 plus c, x n plus c, and the maximal invariant was also derived as either x 1 minus x n and so on. So, various forms can be considered, or x 2 minus x 1, x 3 minus x 1 and so on. So, under the translation group. Okay. Now, if we consider here this group induces G bar on parameter space, that is G c bar theta is actually equal to theta plus c, and maximal invariant we have written, I wrote several different one, but they were all 1-to-1 functions. So, a particular maximal invariant, let me consider, that is say x 1 minus x n, x 2 minus x n and so on, x n minus 1 minus x n, that is equal to say y 1 y 2 y n minus 1. So, y I is equal to x I minus x n for I is equal to 1 to n minus 1. The distribution of t will be independent of theta, and it has density minus infinity to infinity f I y 1 plus z and so on y n minus 1 plus z d z d z. Now, let me call it G, not G, let me give some other notation, say H I of y. Okay. So, if I am considering the density of T, the problem of testing that whether density is f naught or f 1 reduces to testing whether it is h naught or h 1. So, in terms of testing, in terms of T x, the testing problem has reduced to testing H naught, that is H naught versus H 1, that is H 1 that is simple versus simple. So, the most powerful test is then independent of theta, and so it is UMP among all invariant tests. So, by Neyman-Pearson lemma, the rejection region is f1 y1 plus z and so on y n minus 1 plus z divided by f naught y1 plus z y n minus 1 plus z dz is greater than C. In particular, if I am having some known distribution, I can express in terms of that here. Let me take another example, say x1, x2, xn follows say normal mu sigma square distribution. My parameter space omega, here mu is any real number and sigma square is positive. Let us consider the hypothesis testing problem, sigma square greater than or equal to sigma naught square against sigma square less than sigma naught square. Usually, I have considered the reverse of it, that is the dual problem, that is H 1 versus K 1 problem. So, I am taking the reverse of this for applying the invariance concept here. So, if I am considering the translation group that is equal to x 1 plus c and so on x n plus c, where c is any real number, then the testing problem is invariant under G. The testing problem is invariant under G, and the maximal invariant is x 1 minus x bar, x 2 minus x bar, x n minus x bar and so on. There I have written several functions here. However, we can first restrict attention to the tests based on sufficient statistic x bar s square. Then if I look at s square, this is also a function of maximal invariant, because s square is sigma x I minus x bar whole square. So, then s square itself is maximal invariant. If I restrict attention to these two, because here I consider x bar plus c and s square, and if I take c is equal to minus x bar, this vanishes. So, I get s square. So, if I am considering only sufficient statistic, then s square is maximal invariant and we can base our test on s square. Okay. Now, s square by sigma square follows chi square n minus 1, and so the density of s square has monotone likelihood ratio in sigma square s square. So, a UMP test can be obtained among invariant test. So, a UMP invariant test will reject H if S square is less than C, or S square by okay, S square is less than C, and where C is determined by the size condition. This is same as UMP unbiased test, which we obtained in this situation, but here the derivation is extremely simple that you have seen. I will also show for the variance comparison that UMP invariant test is similar to the UMP unbiased test. Let us take say x1, x2, xm following normal mu1 sigma 1 square, y1, y2, yn, another random sample from normal mu2 sigma 2 square, and these two samples are also taken independently. Our testing problem is sigma 2 square by sigma 1 square less than or equal to tau naught against sigma 2 square by sigma 1 square greater than tau naught. For this testing problem, I have derived UMP unbiased test. I also derived the likelihood ratio test. Now, I will derive invariant test here. Let us consider here. So, I define as before S 1 square as sigma x I minus x bar whole square, S 2 square is equal to say sigma y j minus y bar whole square, and consider the group of transformations G of C1 C2. Under C1 C2, this x1 x2 xm y1 y2 yn, they are transformed to x1 plus C1 x2 plus C1 xm plus C1 y1 plus C2 and so on yn plus C2, where C1 and C2 are real numbers. So, here you see xi's are shifted by C1, yi's are shifted by C2. Now, sufficient statistic in this problem is x bar, y bar, S1 square, S2 square, and if I apply this G of C1 C2 on this x bar, y bar, S1 square, S2 square, I get x bar plus C1, y bar plus C2, S1 square, S2 square. So, if I choose C1 is equal to minus x bar, C2 is equal to minus y bar. So, maximal invariant is then S1 square, S2 square. Now, apply a scale group on S1 square, S2 square, that is say G star of say C of S1 square, S2 square, I get C of S1 square, C of S2 square, or C square you can say. Then the maximal invariant. Now, you can see the testing problem remains invariant under all these cases. For example, when I shifted by C1 and C2, there is no effect on the hypothesis here, because mu i's will be shifted, sigma 1 square, sigma 2 square will not be shifted. Similarly, if I am shifting both S1 square and S2 square by the same, then both C1 square, sigma 1 square and sigma 2 square, they will shift to C square sigma 1 square and C square sigma 2 square, and therefore, this ratio will again remain invariant, that is C square sigma 2 square by C square sigma 1 square, C square will get cancelled out and this will remain the same. So, under this problem also, under this group also there is no change in the problem. Therefore, we can consider the maximal invariant here S 2 square by S 1 square. So, if I consider S 2 square by n minus 1 divided by S 1 square by m minus 1, and if I divide this by sigma 1 square by sigma 2 square, this has f distribution on n minus 1 m minus 1 degrees of freedom. So, S 2 square by S 1 square, let me call it z here, this into m minus 1 by n minus 1, this has density with MLR in say tau, that is sigma 2 square by sigma 1 square. So, among all tests based on Z, the uniformly most powerful test is reject H if Z is greater than C. So, this C then you can choose as f n minus 1 m minus 1 alpha. So, this is we have got UMP invariant test, UMP invariant test, and of course, in this case you are seeing this is the same as the UMP unbiased test. What you can observe here is that I have reduced the problem 2 times. Firstly, I am considering location invariance in a particular format, and then I am again applying scale invariance in another format. Using both of this, I have reduced it to S 2 square by S 1 square, which is the reduction which we obtained using the Neyman-Pearson theory, where we had derived the UMP unbiased tests. Now, likewise, one can derive the invariant test for various problems. I will not get too much into detail here. We have already discussed in detail the parameters of normal distribution testing problems, UMP, UMP unbiased and likelihood ratio tests, etc. So, in any of these cases one can also derive the invariant tests. I will in the following lecture discuss a little bit about some related concepts, and then we will move over to the sequential probability ratio tests also. So, that I will be taking up in the following lecture.